Okay. Yes, our next presentation will be by Mr. Mathieu Valat of Martin Fleischmann Memorial Project, entitled Celani's Wire Access Effect Replication.
Thank you. So while we are putting the presentation on, I would like just to reintroduce how MFMP has been created. ICCF-18 last year in Korea, we decided to create a group that it will be doing science on the open. What we heard is that we need a lab-right experiment. We need to expose to the world and legitimize the Lennon field to the science. We also need to have exact replication. That is something that Michael Macru, for example, was requesting. And since Celani was doing his demo in ICCF, we decided to take this experience as the first one to replicate. And hopefully, thank you, Francesco, again, for your openness. This is really something that made the difference in this whole project. We will talk about the loading, the early results we've been doing, the vacuum test we done recently. We will talk about the characterization, the access sheet, and all the questions that will come at the end, and that will be very lengthy. The replicas, I jumped directly to the third one. It's very close to the original. We've been duplicating most of the different parts. How the thing works. Here we have the holder with the mica, Maycore end pieces, same that Francesco was using. Same tube, exactly from the same manufacturer. We tried our best to make that the best replication possible. We added some thermocouple to have gradient along the tube. We did few improvements without changing the original apparatus. So there's two environments. One is in the US, in a lab in the US. The other is in mine. Two different kind of situation where we have one insulated box, and the second is a free air condition. You can see down there. So there's two cells at each place where we can compare directly the two. So this is very important for us to have a control, a kernel control. I'm going to talk now about the loading. So we have decided to use a cycling of power, and I saw that in your lab it's exactly what you're doing right now. It's actually interesting because we have this increasement and variation of resistance when the temperature drops. So when you heat up a wire, the temperature goes up, and when you stop heating it, it cools down. But these wires, when it's exposed to hydrogen, the resistance drop. The opposite thing happened with palladium with deuterium. The resistance goes up. But here, every time we stop putting currents inside the wire, the drop is greater and greater. When you graph that, every time it's restarting to the same level of resistance. So there is no real point in doing that. You can go all the way, and it will load until it reaches the asymptotic curve. So graphed, it's like that. It's pretty much asymptotic behavior, but we guess that it's not exactly high temperature superconductor. It's not a big estimate. This is very interesting, but we don't have much more to say because there is a lot of uncertainties about the loading. This is the most repeatable thing we've been making so far. We loaded something like maybe 8 or 9 wires. It worked all the time, even on toasted light bulb wires. For a few seconds, you try to load it. It's a little bit harsh at the beginning, but it loads still. The resistance drop is quite important. We got up to 26% of resistance drop. I would like to have discussions with people that are very good in material science to explain me that. We have resistance measurement. The resistance when you heat up the wire under vacuum is going up. So the R0 at the original value of resistance is not actually the higher value that will be measured. That's something interesting. So we think about using R prime, to make something different for everybody to understand. And that's my biggest concern is we still don't know what is the relationship between resistance drop and formation of hydrides. That's why we need to do, and the community needs that some time to do this job. It's doing the Baranowski curves for nickel hydride. Yes, Francesco, maybe just a second.
Just information. Recently, people at SFT very recently, people at SFT Microelectronics make a curve with the relationship between hydrogen absorption and resistance decreasing. So they make once the experiment, going to repeat again, and after publish data. In when the relationship little bit remember that of palladium, just remember.
I think that has to be done very carefully and multiple times to be able to have a very good Baranowski curve. If you just have something to remember about this whole presentation, is that we need this. The whole community needs that. We're working more and more on the nickel hydride system. This is basic stuff we have to deal with. This is what I did. Okay. We try to put 50 meters of Vera-Constantin, classic shipping of Constantin that is not treated by Francesco. The resistance didn't change more than 1%, so the treatment that Francesco is doing is actually related to this resistance drop also. It's something I wanted to mention. And we are willing also to talk and open questions about the metallurgical changes that occurs when the hydrides are forming or when the hydrogen is coming into the wire. So if you want to talk about that, come on our website. It's we really have to address these kind of questions. So the early results that have been made at the end at 12 in France, it is very, it's not exactly the original replication, the perfect replication, I would say. Something I didn't expect is the constant I used, and I will explain to you just after on the very heavy loaded graphs, why it became active. The excessive calculated is from the baseline I will show you, but we are pretty sure about the numbers we are having. So let me explain you. Here we have the delta T out in function of the power in. So you have power here, delta T here. So delta T is extracted from the temperature outside the cell, not inside. And we are subtracting the ambience. The first baseline here, it's the first time the commercial constant has been exposed to hydrogen. I made a calibration curve, just increasing power. I have the response, thermal response. Then I did many calibrations. This is the last one, and that is very close to the operating conditions. So we have 1 bar of helium gas inside the chamber, and that gave this red line. So this is still commercial constant. Then I did the loading, so the resistance drop and all that. So I did indirect heating here. So this gives us a variation of external temperature. And computing this, we can say that we got 6 watts over 48 hours. with a power input of between 48 and 50 watts. That's not bad. So we are very happy about these results. This has been challenged a lot on our website. We are still looking for challengers. Come and help us, challenge us about that. Then we decided to use another protocol. This protocol uses basically vacuum as the operating condition. The reason why we use that is because it addresses many questions that our contributors have been making to us. The variation of pressure, the thermal conductivity is changing. We have better reproducibility of such vacuum. The difference between hydrogen atmosphere and helium organ. The higher temperature signal noise ratio. We thought that was a good idea also to use it. And this is basically coming from Cisco. We did at the very end of, it was the 21st of December, you called me, I was having with my friends. Yeah, and you called me saying, oh, I used vacuum, it works. So we decided to use this opportunity, this idea to make a new, full new protocol and work on that. There is also possible variation of calibration between different gas pressure. This is something we have to, it addresses. And there is many questions about convective effects within the cell itself. So the main drawbacks is a shorter operational duration because the hydrogen will tend to come out of the lattice. And do we have the dynamic oxidation? And the answer is yes, you will see. That is my main concern right now. We have here two pictures. So this one below is showing you the wire after it's installed. It has been exposed to hydrogen, heated up. So the surface of the constant, and we have here is a nickel chrome that light bulb. That's why it's blue. But this one is the constant on one, and it was shipped black. After exposure to hydrogen and heat, it went red, which means you just reduce the oxide that was on the surface of it. And when you deload by heating the wire and the vacuum, it becomes black again. So I'm less confident about the numbers when I see this kind of phenomenon because you can really see it and the chemical effect from the oxidation reduction takes place. So that must shake the numbers a little. That is mainly to show you a classic cycle we've been going through. So here you have, after the first loading, that takes a long time to reach the optimal ratio of resistance. You have a very, very fast loading. The best one, I think, was in 5 minutes, we had 16% of resistance drop. If you want to fill a tank of hydrogen, I think it's a good idea, huh? Anyways, this is the real loading, I think, which goes into the grains and so on. And here you have the beginning of the ramp up of power, actually of resistance. We just applied 35 watts of power at 2 millibars vacuum. This is not deep vacuum. In semiconductor technology, we're talking about 10 to the minus 3 ton. If we want to be in a relatively good vacuum, 2 millibars is, there's a lot of people still, but it's better because you can still operate the wire during a sufficient amount of time to have some numbers about the quantity of energy that has been expelled and some other parameters. So the loading time is 8 hours and the deloading is 14 hours. This picture is a SEM picture. It shows the surface of the wire before loading, before any use of it. So you have here the center of the wire, I've been doing a blog post quite lengthy about the geometry of the wire, what we think is happening. This is the coating that comes at the outside. This coating is, you see, it's a pretty smooth surface. Depends who you're talking with. This coating is going all along the surface of the wire, and this is the active material. When we do loading and cycling, we have, and I took a place on the wire that has not been bent or any kind of mechanical stress. But you see there is cracks all along axially on the wire, it shows you that when you have the hydrogen that comes in, you actually are making a lot of these cracks. So I think it's related actually to how the hydrogen loading is going so fast at the beginning, because if you have large cracks like that, the hydrogen molecule comes in these cracks and tends to change the resistance of the wire. I think, I'm not sure. This is maybe something we have to talk about. Sorry. Now I'm talking about the exit. So that's the typical exit we saw on the ramping up power. Here we are putting, so it's the graph of time over excess power. We are increasing the power from 5 watts to 30 watts by step. So we are controlling the DC power supply, increasing the power. And here we have the resistance of the wire that is increasing and more as we go. And here you have the excess. So the maximum is reached at 20 watts, but it doesn't go above after. So even if you are putting 30 watts or so, it doesn't really work better. So if you want to have a good resistance signal-to-noise ratio, that's difficult to say. And here there is this curve. I don't really know what to make of it, but it is interesting because the last value is actually the one you would expect to ramp up and keep going. So at 22.5 watts, we have excess over 4%, beyond confidence level. When we plot the XCC, the run we've been doing, we don't here have an XCC in function of power. We can clearly see there is a temperature effect. The triggering effect is temperature every time you have a big jump. We were very surprised because Francesco, collaborating with us, was giving a lot of hints, and a lot of very good hints actually. Almost 95 or 99% of what Francesco said has been verified. And that is very amazing to see how this was going, because we were not stepping in the dark. So replicating something with the help of Francesco was very easy actually. But this did not verify. We had indirect heating, and it produced more heat than direct heating. Yes, and that was my point. That was my point. We ran the indirect heating before doing the direct heating. So maybe if we had do the opposite, we would have better excess heat. Actually better than the blue one. So what we learned is we have a replication that showed higher temperature than the calibration did. The first one I've been oscillating between 1.4 to 2.5 watts at 30 input. The best yield is at 15 watts. It's exactly what you said, Francesco. The lower values after the first cycle, but Triggering temperature is seen, so that has been shown in the graph, and we're just seeing the same stuff. So I'm going to go quickly through this. I have a lot of things to say, so I'll just let you check that. So we have an open question about thermal conductivity versus pressure, the variability of this approximation of calorimetry. We have it's unlikely to make the same error as the steel and glass cell, which is an evolution we've been working on with Nicolas Chauvin. We have differential tests we want to make, and I think that will be settling the whole question about if there is excess heat or not. The conclusions is we successfully replicated the vacuum protocol that Celani was doing at the end of December. Some wires worked better than the others. Mine actually didn't work that much. I'm pretty sure why, because the nickel chrome wire that was the heating wire inside the cell basically had a big power glitch in, so it turned red, and I'm sure it destroyed the nanostructure on the surface, so that's why it didn't work. We have superficial absorption cracks. I think that hydrogen goes in the cracks, but also leaves at the temperature goes up. And that is, yes, the most important actually conclusion is this one. We need to flux the hydrogen if you want to have excess heat. And we have a lot of work to do. So we're working on the concentration calorimeter with Ryan in Hug in Minnesota. It's actually putting data right now. You can go and check on our website. The steel and glass cell will be back up very soon. It made an unfortunate travel, actually. Partially.
It's loud, but not really.
Yeah, it did a very unfortunate travel. We are on the process, and August will be focused on direct comparison with two cells, one only with nichrome, one with two Celani wires. Same atmosphere, same environment, same power input, same micas, everything will be the same but the wire. And they miss the wire because the Celani wire is black, whereas the other one is shiny. Some new design on the Hubster room, you must have seen that. The high temperature mass flow calorimetry I am currently designing, that takes me a lot of time. Some parallel experiments also, so if you want to test your material, just let us know. It's going to be interesting for us to do this kind of work. We are having new contributors now coming. We are in discussion with quite a few labs. Bob was talking about Queensland University. We have people in Germany. We have more and more people. I wouldn't say more, but there is way more than that. And you, maybe. What do you think? We can ship you acquisition card that will work right on with our system. So just let us know. It's very easy. Thank you.
We are 10 minutes behind. Quick question.
How do you interpret negative excess heat?
Yes, sure. So this is coming from pure calculation. When you increase the power input, we have calibration curves. So we are doing a third order polynomial approximation based on the calibration, the thermal response of the cell. So when we are increasing power, the power goes up very quickly, whereas the calibration curves based on the temperature of the thermocouple outside the cell, here it's not going so at the same rate of the power supply, you see? So the calculations gives negative excess heat, which is normal. The value you want to take a look at is actually where the excess heat settles. These values here are just the subtraction between the computed calibration minus the power input.
Very good. Thank you very much.
Thank you.